तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class we started our study on continuum mechanics, and we had defined what we called as deformation to be a mapping function, okay, and then we defined one of the most important quantities in continuum mechanics, which we called as F, and which we named as deformation gradient Note that we defined this in such a fashion that any line element Tx sitting at x, in other words, if this is the body that we are considering, and if this is a point say x, okay, then, and if this is the dx, okay, and then this dx when the body deforms, okay, then this dx becomes small dx at that point small x, and the transformation of capital X and small x, the transformation which gets you small x, that is this deformation mapping, and the one which gets us this vector d small x from d capital X, that is the d small x, is equal to or given by this deformation gradient F. Okay, this is what we saw. We have not defined the reference configuration. The reference configuration is extremely important in the study of mechanics. There are various definitions for this. One of the major or very important aspect of reference configuration is whether it is a stress-free configuration. Most of the cases we treat a stress-free configuration to be a reference configuration. Now, it is not necessary that a reference configuration should be reached in a body, or in other words, it is not necessary that when we start the deformation, okay, that is a reference configuration, but most of the times in normal instances we define the reference configuration, okay, by this chi naught, where chi naught indicates the configuration of the body when time t is equal to 0, but it is not necessary that this has to be the reference configuration. Okay. Most of the times our successful applications are ones where reference configurations are stress-free configurations. For example, if you are doing say analysis of a human heart, okay, now what is the reference configuration for this? In other words, what is the stress-free configuration? That is never achieved. Okay, in fact, it is very difficult many times, especially in biomechanics, to say what is a stress-free configuration, because that kind of thing will not exist as long as, I mean, in the realm or region of time, that's I mean the time of say for example where we are interested, beating heart, okay, the time at which it is functioning, at that time it may not even reach this reference configuration. So reference configuration is not necessary that it's not necessary that the reference configuration should be reached at any time of interest to us, okay, but you should understand that we need a reference configuration from which we would proceed for further analysis. But fortunately for us, most of the time the reference configuration is defined very neatly for engineering structures, and it happens to be, okay, the configuration at t is equal to 0. Okay. So with that in mind, let us proceed, let us see, and of course we have defined f to be a 2-point tensor and so on. Okay, let us now study more about deformation, okay, and the ensuing quantities. Now, one of the most important quantities that we will come across is what is called as C, okay, defined to be F transpose F, okay, and is called as the right, note this carefully, right Cauchy-Green deformation tensor. And we define B to be, of course these are tensors, we define B to be F transpose, and is defined as left Cauchy-Green deformation tensor. Now look at this, why is it called as right and why is it called as left? The reason is very simple, though people do not understand that. It is just that F is written to the right of F transpose, or it is in the right, and F is to the left, and hence they are called as right Cauchy-Green deformation tensor and left Cauchy-Green deformation tensor. These two tensors are again going to play an extremely important role, and it is very interesting also to see that these two tensors are symmetric. Very easy to see that. So when I take C transpose, look at that, C transpose, then this would become F transpose F, and so it is symmetric. Is that clear? And they are going to also be positive definite. We will not work on it right now, but we will indicate it later. On the other hand, you can't say about F as, of course, as symmetric, because we do not know yet whether it's symmetric or not. From the appearance it doesn't look like that, but of course we had defined the inverse of F, one which takes us from d small x to d capital X. Okay, having studied this, now let us go back and look at what we understand by the term strain. Of course, earlier in this course we had looked at small strains. Okay, now let us look at the strains in a slightly different fashion. You will see that the definition what we are going to put down will reduce to the small strain case under certain conditions. We will just wait for it. Okay, now let us define what strain is. Before we do that, we will stick still to the concept that we are looking at strains as something to do with lengths of material line element. Remember that when we define strain in our say undergraduate programs, we define strain to be just change in length by original length. So the concept that we are going to introduce is very similar, but only thing is that that length what we are talking about is not the usual bar which we had used in our earlier classes. We used to have a bar like that, and that is the bar which we used to define the strains. But here let us look at this material line element closely at every point x and see whether we can do something with respect to the lengths of this material line element. So from that point of view, let us see what is d small x squared minus d capital X squared. Okay, of course this is the norm or indicates the length squareds of dx and d, or magnitude as I said, of d capital X. Now how do you write this down? Of course I can write that down as f dx minus d x squared. Sorry, yeah. Or in other words, this is nothing but, what's this? This is nothing but the inner product, and hence I can write that as dot f dx minus dx dot dx. And using the property of course all of them, I hope I don't leave this, and using the property of transpose of a tensor, this can be written as dx dot f transpose f dx minus dx dot dx, which again can be written as dx dot f transpose f minus I dx, where I is of course the unit tensor. Let me define now E, the Cauchy-Green strain tensor, to be half into f transpose f minus I. So I am defining that to be half into f transpose f minus I. Now look at this term, look at this term and look at this term here, okay, and see what we are trying to do. We are arriving at a strain tensor purely based on the concept of lengths, right. Now of course we saw f transpose f as what, as C, so f transpose f can be written, this can be written as half into C minus I. Now this whole equations can also be written in another fashion. We will see the equivalent of this with our small strain in a minute, but this whole set of equations can be written in another fashion in terms of d small x, okay, d small x. So in other words, I can write that dx is equal to f inverse d small x, okay. Just try it out, let us see what you get. Just look at these equations, substitute that and see what is now the definition that you get out of it. E is defined as half into f transpose f minus I. I am defining E, okay. I will show you how this E is equivalent to that of small strain case when the deformation is small. Just wait for a minute, okay. Before that, let us look at now the same expression in terms of d small x. D small x. So what do you do? Simple. So keep this d small x so that the expression can now be written as dx dot dx, sorry, minus d capital X squared, which can be written as f inverse dx dot f inverse dx, right. And now you can write that dx dot dx minus dx dot f inverse transpose f inverse dx. Yeah, this is the definition of transpose. So you just get, substituting for dx dot f inverse transpose f inverse dx. Now just take that out, dx I minus dx is my original thing, and I define small e called Almancy strain to be half of I minus f inverse, okay, as the what is called as the Almancy strain. Now look at the difference between now capital E and small e. What I have essentially done is to use the definition for transpose, okay. Look back with what we did before. So look at these two equations here. You see that the first equation, the Green strain tensor or Cauchy-Green strain tensor, E is defined with respect to the Lagrangian frame of reference, okay, and this Almansi strain tensor is defined in terms of the current coordinates or Eulerian coordinates. So this is the Lagrangian and this is Eulerian. So the first thing we have done is to define strains. In order to see what is the connection between the large, this we would call as finite deformation strain or large strain, okay, compare this with infinitesimal strain. In order to do that, let us introduce what we call as a displacement vector and talk in terms of displacements and its gradients, so that we can compare, because we know epsilon ij, okay, to be half of dou ui by dou xj plus dou uj by dou xi. So in order to compare both, let us now introduce the term called displacement. Okay, is that clear? Let the displacement u be, obviously displacement u at a point is x minus capital X. That's the displacement. So in other words, if that is the body where it's capital X, Lagrangian frame of reference, and we start here, say for example, most of the time as I said, reference coordinates, and we go to this point x, okay, let u is equal to x minus capital X. Now this is fine as far as both the coordinates or both the systems of coordinates that you use for both are the same, okay, or else you can also write that as chi x minus x. Let me define, many places I am defining, let me define the displacement gradient d to be the gradient of u or grad u. D is equal to grad u. Please note that whenever I put grad with a capital G, it means that the derivative, okay, is with respect to capital X. So this is nothing but dou u by dou x. Note that grad u raises the order of this vector from u to a second order tensor, or in other words, dij is equal to dou ui by dou xj. If I now put, instead of capital G, if I now substitute this in terms of small g, if I say it is grad with small g, okay, then it means that the derivative with respect to small x, which means that dou ui by say dou x j. Okay, so they go together, and this and this, they go together. Is that clear? Now define E in terms of this D. Okay, let us see how you define D in terms of this. It's very simple. I can extend that by differentiating this with respect to capital X. So the first term becomes what? The first term here becomes the deformation gradient tensor F minus the second term becomes I. So D, which is given by this, D is equal to F minus I. Is that clear? Or Dij is equal to Fij minus Kronecker delta Ij. Now substitute this expression here into my definition for E. Please substitute that and see what you get as a result. So in other words, substitute d is equal to f minus I. Just work it out in a minute. Okay, so that it will be a good exercise for you. From here, substitute for f into this expression and see what is the result. So what you do is just f is equal to d plus I. Okay, so f transpose d transpose plus I transpose. So substitute it here and let's see what is the result you get. Half will remain the same. So you will have actually three terms, d as d transpose, then what is the third term? Plus d transpose d. So that's the things you'll have. Okay, these are the three terms you'll have. Now just contemplate on the difference between this and our definition for small strain. Now actually what is this? If you want to understand this, let me write down in an indical notation. Okay, actually I should write capital Ij, but because you're familiar with small ij with respect to small ei, let me write that down. Half into what is this? Dou ui by dou xj plus what's the next one? Dou uj by dou xi plus, how do you write d transpose d? No, it is dou uk by dou xi dou uk by dou xj. Okay, that is the d transpose d.
All x's are in caps.
Yes, you are correct. I should have written it as capital I and capital J, and because I want to compare it with small eij, with which you are familiar with, I'm just writing it for the time being like that. You are absolutely right. All these i's and j should be in capital letters. Okay. X also is capital because if you look at how we defined the displacement gradient, look at this. Look at that here, that you had defined the displacement gradient to be capital G, with capital G. Okay, so that's the reason why you have this to be like that. Now, look at these terms carefully. All of them are capital. Okay, this is capital, capital. I hope it's clear. Now, your definition, if you remember, for Eij was half into ui comma j plus uj comma I. That was the definition for small strain. So see how it reduces. This reduces to that. Once, if small x and capital X are not very different, in other words, deformations are very small, that are infinitesimally small, so that capital X and small x are not very different, then I can replace number one all the capital X by small x. And number two, when the gradients of displacements are also very small, such that the gradient is far less than, say, dou u by dou x is far less than 1, then this term goes off. Okay, so what we say is we have linearized these quantities. Okay, so linearization of my displacement would result in Eij, capital Eij, to be equal to small eij. So in other words, the concept, though it looked initially as if I had defined half, okay, f transpose f minus I arbitrarily, it is not arbitrary. Okay, actually if you look at that closely, I had dx, d capital X on either side, so there is a length scales there as well. Okay, and now you see that it actually reduces to my old definitions here. Is that clear? Okay, so both the definitions go together. Having now defined what is strain, let us now look at what is called as stretch. what is called as stretch. Okay. In other words, what it really means is, my next concept on stretch means that there are different ways in which you can study how a material line element would deform. One way to study it is to define them using E. Another way is to study it using stretch. There are so many other definitions for strains. So strain is not just one quantity. Now itself we have seen capital E, okay, and as well as the other what we called as the Almansi strain. Okay, Almansi strain. Please note this small e is from our epsilon. I should put more epsilon here so that there is no confusion here. Okay, we should put epsilon here. Okay, the small e what we use right now in this course from now onwards will be for Almansi strain. So already we have defined two strains. In fact, there are a number of strain measures as we call it, okay, and we may define them later, okay, for use in certain constitutive models. Right. Okay, but before we go further, we have to define what is called as stretch. As the name indicates, stretch means that the stretching of this line element d capital X. In other words, when I say stretch, obviously what we are interested in is the amount to which, or the ratio of dx by d capital X. What's that? Right. Okay. Now this d small x and d capital X can also be defined by using unit vectors along their directions, or in other words, dx vector is unit vector, say m into the magnitude d capital X. D small x can be defined as m d small x. Is that clear? So that dx, using my deformation gradient tensor, can be written as f m dx. So this can be written as m dx is equal to f m dx. M is the unit vector along the direction which we have chosen, d capital X. Is that clear? Okay.
Is it along the line element?
Yes. Say for example, if this is the body which you are considering, and if this is the point x capital X, okay, and I am interested in this line element t capital X, so that is the line element which I am going to follow, okay. Let capital M be a unit vector along that direction. So d capital X can be written as m, which indicates the direction, multiplied by the magnitude. Nothing very difficult about it.
Sir, one more doubt.
Yes.
We can define the strain by taking the 2 points in the bodies arbitrarily. So is there any difference between this and that? Now we are taking 1 point and we are taking the line element.
Yes.
Whenever we are taking.
Yes.
Instead of that, we take 2 arbitrary points. And
Please note that, yes, I understand. What you are saying is that can I take 2 different points? Please note that we are looking at the situation, it can either be homogeneous or non-homogeneous, or we are looking at a situation where strain, okay, is defined throughout the body at every point. So I have to take an infinitesimal line element. It is not the strain of the total body. It was okay for a unidirectional case. Suppose I take a bar and then apply here, okay, it can be a homogeneous deformation, okay, that's a different thing altogether. But when we take a body, a general body of interest, then we have to take, you can't take the whole body, we have to take a very small region, okay, around the body in order to define what strain is. Please note that in our earlier class we did a very similar thing, but instead of taking this line element here, we took an infinitesimal cube. In fact, what we did was to look at the way this cube deformed, okay, at a point. Remember, all our analysis before was also based on the deformation of the cube, whether we define the stress or the strain and so on. So in this case we are taking a material line element, okay, and the orientation of material line element may change, and accordingly each stretch, okay, would also change, and that's the reason why we have m here. So in other words, as I go to this point x and I take this small material line element, and as I start sweeping it, I may get different stretches. That prompts us to define certain very important quantities like principal stretch and so on. But before we go further, let us now look at what we are going to get out of this, right? Now, so this can be defined here in this case as dx squared, small dx squared, we will take the dot product, okay, inner product on either side, so this would become is equal to fm dot fm fm d capital X squared. So this can be written by using the transpose formula m f transpose f m dx squared. No, this is the capital, small m obviously will go off m dot m. What's m? Because unit vector, we have been talking about that to be a unit vector, so that will go off. So obviously what you will have is only the capital M. So that is, in other words, this is fm dx squared is equal to d small x squared. In other words, we define stretch along m, note that carefully, at a point x along m, okay, to be d small x by d capital X, okay, that is equal to the magnitude of Fm, the magnitude of Fm. So that is what is called as the stretch. Sometimes lambda m minus 1 is called as the extension ratio. It's called as the extension ratio. Is this clear? So stretch is defined, note that, again I am repeating it, note that stretch is defined with respect to m. So when I change m, that is what I just now said, then the stretch would change. This is exactly how you would look at also the small strains. Okay, we had taken a cube such that the faces of the cube and hence its normals are along 1, 2, 3. We defined epsilon 1, 1, epsilon 2, 2, epsilon 3, 3 and so on, okay, with respect to those faces and each expansion. Of course, we defined what are called as shear to be that change in the angle between these faces. So here it is much more general than that. So it is defined with respect to a given m. There also, given any other plane or any other direction, it is possible for me from this epsilon ij to determine what would be the strain in any other direction. Okay. Now how do I define what we call as the shear part of it. In order to define shear, if you remember, we have or we have had, say 2D, we have had two lines, and we were looking at what happens to the angle between the two lines. This is what we were looking at. So in this case, what we are going to do is to take two line elements. Okay, in other words, we are trying to explicitly find out a formula here in this case, what would be the change of the angle of two arbitrary line element. Okay, so in other words, suppose I have, say, let me define that as m and m prime at a point x. Actually, I am just zooming into a point x in a body. Okay, let me call that as capital theta. My whole job here is to find out what happens to this capital theta under deformation. In other words, what is the small theta that is formed at small x, or let me exaggerate that, small theta at small x being the point to which capital X is carried to due to deformation. So these line elements now become small m and small m prime respectively. Right? Okay. So please look at that again. I'll give you a minute. Let us see whether you can think to see how we can find out what is this theta minus theta. So I'm interested in this theta minus theta. How we can find out? Yes, dot product. Please work it out. Let us see where you come to in this. Look at that and look at these expressions. Okay, look at this expression here. Okay, and then just see how you can do that. You correctly said that you have to use the cos theta definition. So cos theta in this case happens to be, if you want, I can write that down. Cos of theta is equal to m dot. M is what? M is a unit vector. Very good. M prime is also a unit vector. So m dot m prime is the cos theta, okay, in this case. And of course, cos theta in this case happens to be what? Small m dot small m prime. But I'll give you a small exercise right now. Now let me see, let me check how you calculate that. Okay, just look at that and see how we can calculate that small m. Small m, this quantity. Fantastic. So that is exactly what I'm looking at. So this can be written in terms of stretch. So what is that? That happens to be f capital M divided by lambda m. Okay. So please write that down. Write it down in terms of the transpose. So have a look at this and write it down in terms of the transpose. So this becomes Fm divided by lambda m, Fm capital M prime by lambda m prime, okay, and then you can write that down in terms of m dot F transpose F m divided by lambda m prime. That becomes cos of small theta. Okay, that's all. So substitute this F m lambda m dot F m prime is that clear? Okay. Now small theta minus, or the difference between them, small theta minus capital theta, is called as the angle of shear. Angle of shear. Okay. Now having studied a line element, and also having taken into account what would be the change in the angle between two line elements. Now let us look at what happens to a volume element and a surface element. They are very important for us later for certain constraint definitions or equations to write down constraints as well as stresses. So let us now look at what happens to a volume element and how that would change under deformation at a point x. Okay. So in order to define a volume element, let me take now at this point same capital X, three vectors say called as dx1, dx2, dx2 or triads of vectors dx1, dx2 and dx2.
In the angle of shear,
Yes.
how we define small m, sir? Because theta, I mean.
Yes, what is small m?
No, actually.
See, what we mean by small m is the vector, this capital M becomes after deformation. This is before, this is a part of the body before and that is after. Okay, so small x is the one to which capital X goes to, and this capital M goes to small m and this goes to.
No, but actually the element is, I mean that point is rotating.
Yeah, of course.
So
okay, if you want you need not draw the graph like that, you can draw the graph like this.
So
Okay,
that way theta, small theta and big theta should be same, because
it can't be, because it is not necessary that these two lines, that's what is shear.
no, because m we can define any in any direction.
No, no, no. This
Reference.
capital M, please note that this capital M and this small, this capital M prime are the ones which we are defining. Okay, these are the line elements. Say line elements, if you are, it's difficult for you to imagine. Just say that you are drawing two lines at a point, infinitesimal lines. Okay, at the point x. So that's what you are drawing. Okay, these two lines you are drawing there, and what you are doing is to follow what happens to these two lines which you have drawn after deformation. Okay, so those two lines now become like this. Okay, let me call that as m and m prime, right? So it is not that small m prime you can draw arbitrarily. It's not arbitrary, but we are following the deformation of this line, and that's why we are interested in the change of the angle between these two. Okay, now let us now look at volume change. Okay, so volume change, as I told you, we have to see not just two elements but three elements, a triad as it is called. So let these three line elements at a point x, they are non-coplanar, of course, they have to be non-coplanar, then only we will be able to get a volume out of these three elements. So the three elements define, okay, volume are say dx1, dx2 and dx3, say at a point x, okay, they define, say that's dx1, that's dx2 and that's dx3, 1, 2 and 3. So that dv from our good old calculus or vector analysis we know to be, so let me put this 1 here so that you don't get confused with the indices. So that 1 means that it's a vector dot dx 2 cross, this is a simple definition, 3 scalar, the result is a scalar, it's a triple product. Now what is that we are going to do? We are going to see or follow, like what we did for that capital M, follow what happens to this d capital X 1, 2 and 3 at this point, so that we will find out now what would be the volume that is defined after deformation by these three line elements, d small x1, small x2, small x3. So after, say, let's say that the body after deformation becomes like this, and that point is now here, and that's small x, and the corresponding lines now, that line becomes dx1, okay, and that line becomes dx3, and this line becomes a dx2. So what I am interested in is to find out what is the relationship between d capital V and d small v, t small v defined now dot dx 2 cross dx 3, right. What I am going to do is again very simple, what I am going to do is to substitute for f. But before we do that, we remember how we calculate this triple product. That is nothing but the determinant, if you remember, okay, dv is equal to nothing but the determinant of dx1 comma dx2 comma dx3. This is the definition for that, this operation. Okay, this is from our vector algebra, maybe in high school level. So d small v is now defined to be determinant of d small x 1, d small x 2 and d small x 3. Now substituting in terms of my deformation gradient, so this can be written as determinant of f dx1 comma f dx2 comma f dx3. Yes, because we are interested in finding out what happens to capital dv, okay, after deformation, that is small dv, okay, that's what we are interested in. Hence we are writing this down in terms of small dx1, 2 and 3, and what happens to this, we get that directly from our earlier expression on deformation gradient, so we write it down like that. So using the concept of determinant of a b, determinant of a into determinant of b, I can write that down to be determinant of f into determinant of dx1, dx2, dx3, which is equal to dv. So we come to a very important relationship now, which states that d small v by d capital V, the ratio of the volumes at a point, is given by the determinant of the deformation gradient at that point. Please note that all these material line elements are very small line elements, okay, so you can say that this would give rise to that small volume change, okay. Imagine that if you want to be a cube, okay, and what happens to that. Now if the material happens to be incompressible, then what would happen? D small v is equal to d capital V, or determinant f, many times written as Jacobian or J, okay, that it happens to be equal to 1. So having seen how deformation of a small line element takes place, let us look at how a surface element deforms under loading in the next class. We will stop here, we will continue in the next class.